I kind of had a thought. I mean, I want you to become the kind of students that you write down, you take notes the way you need to. Sometimes that is whatever the teacher does, but it doesn't have to be. So, there was some explaining with this problem, but I kind of added this, and I'm just wondering, did any of you add something like it? Do you feel like you want to? So we've got a hole in the graph, but again, the y value intends to be 1. Okay, so some of this I know you're kind of listening to, and we're just writing down answers, but we're talking about the reason. You can always say extra things, or you can just listen real carefully. That's actually what I want to do now. I want to show you a little video. Okay, now, probably not a great time to get up and use the restroom, because the video is supposed to enhance what I taught you, and even there'll be some new things. So make sure that, same thing, that you're listening. I don't know if you need to write anything down from it, though. I will actually write something down and wind up doing a problem near when it's over. But just kind of watch. You're going to hear some of the same things. You're also going to hear some things enhanced a little bit. And maybe you'll even think it's a little funny.
You may have heard a lot of talk about limits, but the plain fact remains, most people don't understand what a limit is. So for now, we're going to focus on what is a limit. In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a function. Now, this might give you pause. You might think, how am I supposed to know what height a function intends to reach? I don't even know what my intentions are most of the time. How am I supposed to discern the intentions of a function? That's a good question. And the fact that you don't understand exactly what I'm talking about is because all of the functions you've been dealing with, or at least most of them, have had their intentions completely clear. If a function intends to reach 3, it reaches 3. If a function intends to go 6 units high, it goes 6 units high. There hasn't been a lot of mystery so far. So I understand that you might be a little confused, but you've dealt with function heights a lot. So we might as well review function heights a little bit and then get into exactly what I mean by intending to go to a certain height. Let's start by looking at a very simple function graph. What I have here is the function f of x equals x squared, basic parabola. You'll notice that the function changes heights all throughout its domain. That's a very fancy way of saying that the function reaches many different heights based on whatever the x value you're looking at happens to be. For example, what if I look at the function height that corresponds to x equals 2? Well, it's not very difficult to figure out exactly how high that function is going to be when x equals 2, because all I have to do is plug in that x value into the function to figure out what that height will be. So, if I plug 2 into x squared, I get 2 squared, or 4. This means that the function reaches a height of 4 whenever x equals 2. Pretty simple. But now I can create my first very basic limit statement, and that is a limit as x approaches 2 of f of x equals 4. This just means that whenever I am getting very close to the x value of 2, my function is getting very close to the height of 4.
Now, there was something new that was shown in there. It wasn't meant to be hard, but it was something new, and that is that you can substitute. You can plug in x values to get the y value. Again, you know that that's basic math, but using a substitution method is a valid way to find a limit. Okay, again, just plugging in x to get y.
There's nothing really earth-shattering about what we just learned. But that changes when we examine functions that do not reach the heights they intend. Take, for example, this function. G of x equals the fraction x squared minus 6x plus 8 divided by the quantity x minus 2. Here's what the graph looks like. It looks like a plain old line. Or does it? If we zoom in, you'll see that it has a hole in it at the coordinates 2, -2. The hole exists because plugging x equals 2 into the function results in 0 divided by 0. And we know that dividing by 0 is a very bad idea. It breaks mathematical laws that we really can't even get into here. However, though this graph has a hole in it, it still possesses a limit when x equals 2. Clearly, the graph intends to reach a height of -2 when x equals 2. Even though that graph doesn't actually reach that height, it doesn't matter. The limit still exists, and we can say that the limit as x approaches 2 of g of x is equal to -2. This begs the question, when exactly does the limit exist? We examine that in the next module.
To maybe quote or paraphrase one of the last things he said, even though the graph does not reach a height of -2, it doesn't matter. It only matters that it intended to get to that height. Now, I want to take that problem and kind of do it with you in show you an algebra way. Okay, so it's the same problem to solve. But really my purpose here is to show you the algebra. So it's up here. All right, so it was the limit as x approaches 2 of x squared minus 6x plus 8 all over x minus 2. Now, as was shown in that basic parabola problem, substitution can be a valid method. It can be, as I like to say, kind of your first line of defense. And so substituting in the number 2, at least the idea of doing that is not a bad idea. Okay, because substitution, plugging in x values to get y values, is a valid method. Now, he did this. He just kind of did it quickly. I just want to give you a chance to kind of process this. It's pretty easy to see that the bottom is 0. It's also, but it's interesting to see that the numerator also becomes 0. You have to do a little bit of mental math there, but ultimately you get -8 plus 8, and so we get 0. Now, we're going to talk more about 0 over 0 tomorrow, but it doesn't hurt to hear it today. That's known as an indeterminate. Okay, it's an indeterminate. What that means is it does not determine anything. Okay, and again, it doesn't hurt to hear this a couple times. What I'm trying to tell you is that that does not tell us the limit. It doesn't mean the limit is no solution or does not exist or some other idea. It just doesn't tell us anything except to turn around and do something else. Okay, so we kind of turn around, we go back to the original equation, and we try something else. And now, maybe we think a little more about some algebra that we've learned. What do you mean some algebra that we learned? Well, now that I mention it and try to get you to focus on the numerator, x squared minus 6x plus 8, x squared minus 6x plus 8. Are you feeling like some algebra? You know, how could you change x squared minus 6x plus 8? How could you change it? All right, you could factor it. You could factor it. My youngest son is working on some factoring in 8th grade. Boy, he loves it. But you just got to find the right combination of numbers. I know students have been taught this different ways. but sometimes the most basic way, just two numbers that multiply to be 8 and add to be -6. Two numbers that multiply to be 8 and add to be -6. Maybe I'm not telling you something that you don't know, but I am trying to get you to think that you can factor it. Okay, still feeling like some algebra? Still feeling like some canceling out of these common factors? Now, back in your trig class last year, you may and you should have, but if you didn't, whenever you have this effect, it's called common factors. Whenever you have common factors canceling, that's a telltale sign that there's going to be a hole in the graph. Okay, remember his little silly, or does it? It looked like that it was a line, but it had a hole in the graph. Okay, that's because these common factors are canceling out. In terms of limits, which is today's conversation and tomorrow's and the next 3 weeks, but in terms of limits, I now have the ability to plug in and get a y value. Like now I can actually plug in the number 2 safely. When you look at that, it's the y value. It's the limit that he showed up on the little video. Algebra, substituting. Okay, nothing was wrong with that. It just gave us something called an indeterminate. I'll show it to you again tomorrow. It does not determine anything except to say turn around and do something different. In this case, different, we could factor. Okay, I say in this case, we could factor, and then we get something that we can plug into. In other words, we get a result that is not something weird like 0 over 0 or some other things that I'll show you. Okay, but the whole idea here is that we found the actual limit of this function. Now you might want to have a copy of this function. It's the same graph he showed, just without the silly sound effects, but it has a intended height of -2. Okay, it has an intended height of -2 as x approaches 2. Okay, to kind of write that out with some simple words, as x approaches 2, y intends to equal -2. Okay, now there'll be a time in a couple weeks where you'll start to realize, why do we have limits? Okay, why do we even have an idea of a limit? And a simple answer today is we don't like that hole in the graph. Okay, it's kind of like messing up the graph. So if we know what it's intended to equal, we can fix it. We can fix it. We can basically fill in the hole with the limit. Okay, so again, think about limits. They're like intended values. We can use an intended value to actually fix a time when there is no value. Okay, and there'll be more, but that gives you a little bit of a taste of kind of where this is headed. Okay, it's a good stopping point. We usually have gone. I've taken guys up to the bell. We don't need to do that, so it's a good stopping point. And we'll keep talking about limits tomorrow.